And of course, you're all very smart, and you're thinking, wow, I can do this easier. I can just get a dictionary of things and try to map things to the dictionary. So this is what you have a thesaurian. Yes? Sure. This one? Or the cats? Yeah? Yeah. Yeah, so what they do essentially is they... Yeah, what they do... Yeah, sorry, I didn't express myself. I'm going too quickly. So what they do is they remove the dots, and they just search for cat without the dot. And the first result was a lolcat. Right? So it's like you don't index this thing. You don't recognize this entity here, this string, as a word per se, because you are normalizing the word. So you just, take the dots out if they're have these rules. Yeah, but there you go. Something we were better at. Anyway, so some other people have tried to build by hand equivalence classes of words. So like car and automobile and color, British against American spelling are the same. So you can rewrite a lot of these things. This is very time consuming. It doesn't scale up. But you might try to do it. You can try to do this automatically, like trying to get equivalence classes based on phonetic heuristics. So people tend to write how they think something should sound like. So you can try to expand the representation using this sound thing. But it's fairly unusual. Anyway, more lemmatization. So instead of indexing am, are, and is, you index be, the head word form. So you have these classes, right? So this is like lemmatization is proper language natural language processing techniques, and it can be very expensive to run, but still you can think of doing this if you don't want to, bother by doing stemming, which is what we're going to see now. So maybe you're all lost now. But why are we doing all these things? Why are we trying to say that two words are the same? Why are we trying to conflate all these representations? And it's sort of because people are going to enter this query, this word, and you want to say that this document is about this word. So if you don't remove, for instance, the plurals, the S, and you enter the query house, if a document only says houses, you will never match the document. You will never retrieve it as a potential candidate, and you really don't want that, right? So all these techniques are for that. And stemming is possibly the most aggressive technique for doing that. Just, again, heuristic, which is great because it's fast. What stemming does is that you reduce the terms to their root before indexing. And you can think of it as like very crude language-dependent rules. Like you say, take the S out, you take the IC out, you take the ION out, and you put all these three words, automatis, automatic, automation in total. So a text like this, for example, compress and compression are both accepted as equivalent to compress, will look like this to the machine. For example, compress and compress are both, you can read it. And these are what the terms that you put on your search engine. There are various ways of doing stemming, but the most efficient one is just doing the removal of the affix, right? So the last part of the word. And one very popular algorithm is Porter's algorithm. There's also things that uses lookup tables with kind of handcraft made rules, like play plus ing go to play, but the table can be huge, and again, you want to be fast. It might not be practical. Now here, the problem in general with stemming is that you might be creating false positives. You might be saying that organization and organ are both org, which is wrong, right? But then again, you can put heuristics on top of the heuristics to deal with these cases. Now, we have this precision and recall discussion, right? So precision is how good you are, at retrieving documents, and recall is how many documents you retrieve for a particular query. So you think stemming is good for precision, good for recall, bad for precision, or bad for recall? Very good. Essentially, a safe answer always is, if it's good for precision, it's bad for recall, and vice versa, in general. But that's correct. So you are increasing the recall. You are increasing, the span, the match span of the query. But then you might be failing on some cases like this. So that's why you have to be careful. So Porter's algorithm is just rules. I mean, I just show you an example. So you have things like that, right? This turns into this turns into this turns into this, and so forth, and so forth. These rules are applied in cycles. So there's like 5 kind of sequences of rules that you apply. But nothing more particular than that. There's also cases where you want to say, well, if the word is very, very short, then don't do anything, right? Because you're going to get it wrong. So you can also have rules that are dependent on the length of the word and things like that. Again, it's language specific, stemming, and in many cases also application specific. In many cases you don't want to do stemming. Or maybe in the case of web search, you want to have stem terms and non-stem terms, but then that creates the tension on how do you rank documents. We have all these things there. Again, there are open source software for doing this rather effectively for a lot of languages, so you might want to look into that. So does it help? So for English, it is a bit mixed. But for other languages, it's great. So like Finnish, for instance, you get a huge boost. And this all depends on the characteristics of the language. So it helps for Spanish, it helps for German, it helps for Finnish, maybe not so much for English. And then using a thesaurus. So I want to bring this up because it has a lot to do with semantic search. And it's essentially saying that, if you know that the bank in the document talks about the finance institute and not the river edge, then you just link it to this entry here. Right? And now you're putting semantics in place. Okay? And hopefully you'll learn from Ed how to do this thing efficiently tomorrow. That's pretty smart. I can make the search engine look pretty smart already. Right, done with representation. All this is very important because if you want to get the search engine right, this matters a lot. Most of the performance is already there. Now, how do you store all this information? This is a topic on its own. I could talk about that for hours. You don't want me talking about that for hours, believe me. But the main problem is how you keep fresh copies of the web that can be managed by a cluster of computers, and you can answer millions of queries in milliseconds. That sounds pretty hard. But essentially, like the cornerstone are inverted indexes, and I'll show you a picture of a cute inverted index right now. But this is, like the basic data structure that has been in there since mid-90s, I think. Also, compression helps a lot when you're talking about compression, but compression is a big deal because compression not only lets you store all this data in a reasonable amount of space, but it also lets you have more free main memory for other operations like caching. Right? You can put more, if you have a more compact representation of your document, you have more space for the cache, and that's very good. So what is an inverted index? So it's just very simple. So for every word, every term, all these guys that we identified before, you have to store a list of all the documents that contain the term. Okay? Like in a book. When you go to the book, to the appendix, you have all this list of terms that says, this concept is on page 55. So it's the same thing. So documents are identified by a document identifier. That's very straightforward. And building this index is very tricky. Right? We won't get there. But as I said, the problem of building this index in a distributed fashion, in a reliable way, gave rise to MapReduce. Right? And the way of so the problem of updating this index, it gave rise to things like NoSQL databases and things like that. So all these cool tools that we have now come from this very basic problem, which is creating this index. So it's definitely an interesting topic. So this is an inverted index, right? So this is your collection, right? So you have the documents, and these are the terms. I'm just putting a matrix. So you know when you process this document here, you find this guy, T1, you don't find T2, and you find T3. All right? Same with D2, same with D3. So essentially it's like an incidence matrix. You could also have the number of times that you find the term here, right? This is for the sake of simplicity. Now you invert this. So now you have the term as a key and the documents as the values. Right? So term number 1 is in document 1, 2, 3, 4, it will be 5, 6, 7, 7, blah, blah, blah. Right? So same with T2, same with T3. Okay? Super simple, but this is the key. You can have more stuff there. Essentially, there's two big pieces. One is the dictionary, which actually keeps the actual string. That's also compressed because it has to be kept in main memory. And then you have the term ID, which is a number that you assign sequentially or whatever. And then the document frequency, which is the number of documents that contain this term. So you know, for instance, for A, it's in 4 documents, this is in memory. And then traditionally, this will be on disk. I'm not sure about that anymore, but you can think that this is a huge structure and this is very small. So you go to disk and you know that A is on document number 1, 2 times, on document number 2, 5 times, 10 1 time, and 11 1 time. Okay? And of course, this structure is compressed and it's super compact, and the data access is very controlled. And, because what do we do when we get a query? So we go to this structure, we'll see later. You can put more information there. For instance, you can put here the position in which the term appeared in the document, right? So this document was this term was the first term that is seen in this document. And this is very useful for phrase queries, right? When you put quotes, you want this thing that appeared consecutively in the document. So to match these things, you need positional information. You can also put the fields in which the term appears. So you know that this term appears in the title, this term appears in the body of it, in the anchor text. You can also put metadata and payloads of information here, right? All these, so essentially when you put positions, like the size of the index is like 5 times larger. But sometimes you have to do it. And the cool thing is that all this information can be used for ranking, for deciding which is the most important document for your query later on. So now, super quickly, because you already figured out. So how do you solve a query? How do you process a query? Well, there are several kinds of queries. You can have Boolean operators like and, chicken and salt, or genome or KDE, or salt and not pepper. So you have and or and not. You can have phrase queries. Just find me these things, but they have to be together. San Francisco, New York, pizza, New York has to be together in the document. Or ranked, which are the most interesting ones, which are like typically associated with keyword query, which is what we input in search engines these days. So how do we decide which are the good candidates for, or the documents that match, that satisfy a particular query, right? So if you have a Boolean query, then you have chicken and curry. So you go and locate chicken in the dictionary, and you go and get the postings for chicken, right? You got this list now. And then you go and locate curry in the dictionary, and you get its document list. And then you merge both lists. Right? So we'll see an example now. So this is the algo for this intersection. Now, of course, it's not as simple as this, but this is the basic idea, right? So you open these 2 posting lists, or P1 and P2, and you iterate until you're done in one of the lists. And whenever you find the same doc ID in both posting lists, you put it into your result set. You have a structure, a queue, whatever, you put it there. And then you advance the pointers. And then otherwise, you advance the lowest pointer. Right? I think this is, you see it better like this, right? You have salt and pepper, and you want to intersect them. So you open the pointers, you have 3 and 3. Oh, 3 and 3 are the same. Great. Put them in the result list. Advance both pointers. You have 22 and 5, although not the same. So you need to advance the lower pointer. So you advance 5. You have 22 and 22. Awesome. Put them on the result list. Advance both. You have 23 and 25. Then you have to advance the lower, which is 23. You get 25 and 25. they concede. And then you finish up here because there's no more items left, so you're done. Right? Simple. There's a lot of tricks to speed this up, as you can imagine. But like, this is the basic operation of a search engine, intersecting these things, or finding the union of these lists. Right. So I think we're done. We can have a short 5-minute break or some questions. Anyone alive out there? Hey? Still alone? I know it's late, but I ran out of jokes on the slides though. All right, so just 5 minutes, 10 minutes, and then we kick it out with the rest of the talk. Yeah. Yeah. A couple of them. Right. Hola, hola. You hear me in the back? Is this on? I'm blind. Ah. All right. This is the last part, which should be, if you ask whoever what is a core course lecture information retrieval, it would be this part, I guess. Not this one. So I think we're going to just touch upon a lot of concepts that you need to understand more or less the next lectures, but not going much in depth. So models of information retrieval. So what is a model? So a model is an abstract away from the real world. Right? So a model is something that uses a branch of mathematics in order to try to represent a concept into an equation. And possibly you use a metaphor for searching. You make some hypotheses, some assumptions of why people search in a particular way, and you try to incorporate and implement these assumptions in the model. Brief story. I could have started with this, but this is much, much boring than the web search engine story. So first there was the Boolean model in the 1950s, which is something that we already talked about a bit. And then right after, people started to try to figure out what made two documents look alike. Right? What is the document similarity, text similarity metrics? And that sort of gave rise to the vector space model, which is sort of like the foundation for most information retrieval models. Then there was probabilistic information retrieval that came right after, which developed in language models. I think you will be hearing a lot about language models later on. And linkage-based models. I'm talking about PageRank here. I will not explain how PageRank works, but this is here. And now we're looking into much more complex models. So things that take into account the position of the words in the document, or if a word occurs in a particular section of a document, right? So there will be fielded models. I won't get deeply into that. But as a takeaway, if you want to leave now. So the things that are important for retrieval modeling are term frequency, which is the number of times the term occurs in the document. Document frequency, which is the number of times the term occurs in the collection, the number of documents that contain this term. Document length, which is the number of terms in the document. And that's it until 1998 or 2000 or even further. That's it. Just these three ingredients. And you mix them together and you get all this information retrieval stuff. Now, I guess in 2005, we started to look into other sources, which is where exactly the the term appears in the document. And if you get a query that is formed of many terms, if they are closer or farther away in the document. Right? So you want to surface things that are closer in the document. And this is the summary. I mean, there's just equations, the rest, and how you get to these equations. A Boolean model, we've seen that before, right? So essentially, you know how you want to build your query. You want this term, you don't want this term, and you want maybe one of these two terms. So you do and or and not, intersection, union, and difference, right, of sets. So this will be, you have three words, you have social, political, economic, these are Venn diagrams. So you want social, and economic, then these are the documents that are going to match your query. If you want social and political and economic, it will be this little thing in the middle. If you want social or political, but not economic, it will be this set here. So, I mean, you've seen this in, when you were like 10 years old, I guess. Now, this is fine, or this used to be fine. But then there was this idea of similarity between documents, which was brought up by Lund in 1957. And essentially, he's saying that the more two representations agree in given elements and their distribution, the distribution is the number of times you see a particular element, the higher will be the probability of them representing similar information. Well, this is pretty simple. It's saying, if you're using the same words, then you're probably talking about the same thing. Okay? It's pretty reasonable, but up to this point, was nothing formal than that. So it is proposed here, this is from the paper, that the frequency of word, term, occurrence in an article, this is now we call document, furnishes a useful measurement of word significance. Essentially, that's what we're saying. If you're using the same words, you're talking about the same thing, but in a very poetic way, like research paper kind of way. But that's just that. Now, Zipf's law, and I hope George doesn't jump and try to attack me here. This, even if there's some disagreement on whether it holds and in what context it holds, is a very important law. And it has made, it has kind of implied a lot of decisions in the way we model stuff, information retrieval. Essentially, it says that have the frequency of terms, like the number of times you see a particular word in a collection of documents here, and you rank them by order, right? So here is the frequency of the most frequent word, and the second, the third, the whatever, ta, ta, ta. So you follow this curve here, all right? This curve is a power law, say, and it kind of arises in a lot of different scenarios, some that you wouldn't expect. But essentially what it says is, again, there are a few very frequent terms and very many very rare terms, right? So essentially the law in its crudest form says that the ith most frequent term has frequency that is proportional to 1 over I. Essentially, in a mathematical way, is that the frequency is equal to k divided by I. And the interesting thing is that it holds for different languages. But it also holds for other situations, as I said. For instance, if you take all the queries that arrive in a search engine, right, and you count them, so you know that these queries are very Facebook, right, Google, that are very frequent queries, and you do the same thing. You sort them and you put on the y-axis the frequency of occurrences of the queries, you get a similar shape. Again, what it says is that if the most frequent term with the occurs x times, then the second most frequent term, which will be of, will occur x divided by 2 times. And then the third most frequent term will occur x divided by 3. And equivalently, it says that the log of the frequency is the log of a constant minus the log of the position. So you call this a log-log linear relationship between frequency and order. This is yet another power law. And this is sort of how it looks like. So the straight line is how it should look like. And this is how it looks like in reality. So there's some interesting deviations from the predicted distribution, which make a lot of people think very hard about this problem and angry about it and upset about it. Anyway, so another observation from Lund, or Lund, I don't know how to pronounce it, is that you want to say, you just said that if words are the same in the documents, then the documents are talking about the same thing, but some words are essentially more powerful than others in deciding if two documents are similar, right? You have two documents that talk about Bangalore Summer School 2013, and they have these words, that they're talking about the same thing. You don't really need to look at the rest of the document and to know that they're the same, about the same topic. So what these researchers said is that terms have resolving power or discriminative power. So this is the ability of terms to discriminate between document content. And what it says is that you have the Zipfian distribution here. So you have very common terms here, and you have very rare terms here. This is called the head. This is called the torso, and this is called the tail. So the guys that you actually want to pay attention to are here. So very common words, you don't care about them. And he's also saying that very rare words, you shouldn't care much about them either. Although all retrieval models that I'll talk about, and possibly most of the baselines that are used in the R community, they don't take into account in this consideration. So it doesn't really matter. If it's the rarer, the better. So as I say, these are the good guys. I guess I already said. Now let's go back to Boolean retrieval. Imagine you can issue the perfect query. You know really what you want, and your user knows how to express the query with Boolean. Yes? Oh. So yes, so what he was thinking about is that those are spurious occurrences, like typos. And if one thing occurs just in this one document, then it's not to the user. So what does she do? Because you cannot tell with Boolean queries whether one document is better than another. Again, nowadays it's very difficult to get users to write Boolean queries. So you expect the keywords to work out of the box. But this wasn't the case until the mid-90s. And people thinking that you shouldn't write Boolean operators, that was like a heresy. Now, the problem with Boolean queries is that you either have too few or a lot of results. So think of a query like standard user dealing 650. You have 200,000 hits. But then you add no card found, and you have 0 hits because there's no document with these exact words in there. It also takes a lot of skill to come up with a query that is actually reasonable to handle, like the results are reasonable to handle. So we don't want this. Right? We want rank retrieval models. So we want, instead of a set of documents that satisfy a query expression, which is this Boolean model, you want to order the document. You want to say this guy is actually more relevant for your query than this other guy. This is rank retrieval. And this is what we expect right now when we use a search engine. So, as we said before, now users just look at the top K results. Let's say K is 10. I mean, they never go further than 30. They never click past the third page of results. We don't want to overwhelm the user. So the premise is that the ranking algorithm is going to work to some extent. Right? So what you're looking for, it has to be in this head top set of documents. So scoring, this is what we do it. This is how we do it. So we just assign a number to every document for the query, say in between 0 and 1. It doesn't have to be, it's not in between 0 and 1 generally, but it can be think about it between 0 and 1. And this score has to measure how well document and query match. Okay? This is what retrieval modeling does, tries to come up with this score. So how do we do it? Think that you have just one term query. So something reasonable is that if the query term is not in the document, then 0. I don't want you to score 0. And then something other intuition that is reasonable is if this query term is many times, occurs many times in the document, then the document really must be about this term. So it's like a very naive and crude representation of human cognition, but it kind of works in practice. So in general, most of your approaches use the bag of words model, and everything I'll be talking about today uses this. It essentially says that you don't consider the ordering of the words, you don't consider the positions, even though there's ways of doing that. So essentially, John is quicker than Mary, and Mary is quicker than John, is the same. Okay? There's no way to differentiate these two in these models. They will always get the same score for any query. And that's called bag of words, because it's like you have a bag and you put all the words there and you don't know where, the order in which they were to begin with. So as again, I said important signals, term frequency signals. Number of times the term is in document D. Essentially, we said, the more times you occur in the document, the better. Now, a document that has 10 times the term is more relevant than a document that has the term just once. Makes sense. But maybe not 10 times more relevant. So you don't want a linear relationship between importance or relevance and term frequency. You want something that saturates, something like this, sort of like a logarithm, or sigmoid, or machine learning people. So relevance does not increase proportionally with term frequency. This is key. I mean, this has been one of the key, to me, ingredients in making these models successful. Right? Just modeling this proportionality between the number of times you see the term and how important it should be. So something very crude will be, just take the log. Okay? So you have the score you have for this one word query is going to be the log of the number of times you see. So if you see the guy 0 times, then you got 0 score. If you see the guy once, then you have a 1 score. Then but if you see the guy 1,000 times, you have a 4 score. Okay? So this doesn't grow linearly; it just grows. So it kind of saturates in the right end. So essentially, in the end, this is the one simple formula based on term frequencies. And your simplest rank retrieval model. It is for every term that occurs in the document and in the query, you sum the number of times. So you sum the 1 plus the log of the number of times it occurs in the document. All right? Super simple. Now, how can we get beyond this? Well, we can incorporate Loon's findings into this, which is rare terms are more informative than frequent terms. So if this term is used by every other document in your collection, then maybe possibly it's not very discriminative for determining if the document is relevant or not. So consider a term in the query that is rare in the collection. So arachnocentrism.